Hello chemistry students, this is Miss Shirley. This is my first video for our modified flipped classroom, and today we're going to be taking notes over nuclear chemistry, reactions of the nucleus. As you're taking notes, please make sure that you have your guided notes out in front of you. Your guided notes are the ones that I gave you guys previously. So here are your notes. We will be going through all of the first page on nuclear chemistry and our types of radiation, and then we'll also cover some nuclear decay practice, the half-life, fission and fusion, and then applications of nuclear chemistry. That'll be on a separate video. So let's go back here to our notes. Alright, so in our lesson so far, we have been learning about atomic structure. What are the parts of the atom, the nucleus that includes protons and neutrons, as well as the electrons that are orbiting around it in different shells. Today we're going to be talking about those isotopes and the reactions that they undergo over so much time. So we're also going to be talking about radiation in this video, and I'm sure that you've heard of radiation in different parts of your life. So let's go ahead and begin. So the isotopes, we know that isotopes are atoms of the same element, they just have a different number of neutrons. And these isotopes are actually, they can be unstable. And it really depends on their setup. So it really depends on how many protons and neutrons that they contain in their nucleus. So, when these isotopes go through reactions, here are some things that occur. So the difference between a nuclear reaction and a chemical reaction. With a nuclear reaction, we're creating new elements as our products. And I'll show you guys some examples of that later on in the notes. With a chemical reaction, elements are never formed. However, the compounds that we started with have just been rearranged to form different compounds. So maybe one of your reactants that you started with was sodium chloride. Maybe a product that you create is hydrochloric acid, HCl. So again, with a nuclear reaction, new elements are formed. Chemical reaction, elements are just rearranged. And when I say new elements, I'm not saying that we're creating new elements on our periodic table. We're making elements that we didn't start with as far as a reactant goes. Nuclear reactions only involve protons and neutrons, whereas chemical reactions will involve movement of electrons, and those electrons are our outermost electrons in our shells. Nuclear reactions involve a large amount of energy, whereas chemical reactions much smaller amounts, and we can actually do those in our lab. Finally, nuclear reactions, the rate of the reaction is not affected by temperature, so we can't heat it up, we can't add pressure to it, or increase our concentration to get that reaction to increase. Whereas a chemical reaction, we can. We can add heat, we can increase the temperature, we can increase its concentration, making it less dilute. We can increase the pressure, and the speed, how fast that reaction occurs, is going to speed up. So there's kind of your comparing and contrasting T-chart for nuclear reactions versus chemical. So again, let's go back to our discussion on isotopes. So stable isotopes will not decompose over time. For something to be a stable isotope, it has to have a ratio of 1:1 protons to neutrons. So if it has an equal amount of protons to neutrons, it's not going to decay over time. It is stable. It's going to stay that isotope forever. However, the further away that ratio gets from 1:1, the more unstable that isotope is, and the more it's going to want to decay. When I say decay, that I mean it's going to go through that nuclear reaction and become something different. It's going to become that new element. So again, unstable isotopes, they will decompose over time. We call that process of decomposure radioactivity. Isotopes that go through radioactivity are called radioisotopes. So that means that they are unstable and they will decompose over time. An adjective you could use to describe them would be that they are radioactive. Lastly, the particles that are given off during that decomposition, when those isotopes break down, they decompose and they produce particles. Those particles are called radiation. Now, this is probably something you've heard of, especially if you've had any members of your family or friends that have gone through cancer treatments. Cancer treatment is usually a combination of chemotherapy coupled with radiation. And so what happens is the patient would go under a tool that would produce radiation, and that radiation hits their skin, kills off those cancer cells. You've probably also heard of it through the sun. We receive radiation every day when we're exposed to the sun. However, we've got our ozone layer that protects us, so we don't get too much radiation. So it's a good thing, it's a bad thing. It just depends on the purpose that you're wanting to use it for. All right, moving on. Okay, so as far as looking at our periodic table, if you are looking at atomic number 83, should be bismuth on the periodic table, every isotope after bismuth is going to be unstable. So any isotope before bismuth is stable. So again, anything after bismuth, if it is an unstable, or if that ratio is not 1:1 after bismuth, then it is going to experience radiation and it's going to decompose over time. Now, there's different types of radiation that occur, and that's what we're going to be going through in the next few slides, or this few different types. We're going to skip half-life for today. So here are the 5 different types of radiation. The first is alpha particle emission. The main property there is that your products are helium nucleus. Beta particle emission, or beta radiation, produces an electron. Gamma radiation produces a high energy photon. And if you remember photons, those are light. That's a pocket of light energy. Positron emission, this produces a positron, which is kind of like a positive electron. And then the last type is electron capture, where the nucleus actually captures one of those electrons that are orbiting. The 3 types that I want you guys to know about are alpha particle emission, and we notate alpha particle by this little Greek symbol. This is alpha. So the alpha particle emission, and again, alpha particles emit a helium nucleus. So if we're writing it as a nuclear equation, you're just going to have helium. And remember, we have our atomic number 2, our mass number of 4. Now, the only thing that can stop these type of particles, this alpha particle is not as strong as some of the other types of radiation, so paper actually can stop this type of radiation. The next type is our beta particle, or beta emission, and again, this produces an electron. And how we're going to note what it looks like, we're going to have an E, -1, and a 0. Because remember, electrons, when we lose an electron, that's going to change the protons that we create to be -1. They will not affect our mass number at all. Now, beta particles are a little bit stronger than alpha particles. The only thing that it can be stopped by is lead, and then anything stronger than lead can stop it as well. The last type is gamma, and again, this produces a high energy photon, that pocket of light energy. We denote it as +1, 0, and an E. So our protons will actually will gain a proton here. And this is the strongest type of radiation of these 3. It actually can only be stopped by concrete, and then anything stronger than concrete. So gamma radiation is typically the radiation that cancer patients are receiving, is gamma. All right, so a few more examples of these different types of radiation. So this is through alpha emission, and the isotope that is unstable is uranium. Okay, on your periodic table, it's 92. So if you look at your periodic, let me pull up a periodic table real quick. So uranium is actually down here. Here it is, uranium 92. So notice that number is past bismuth. Here's 83, right? So we know that this is going to be an unstable isotope. And when it decays, again, this is how it decays through alpha emission. So we see it on our reactant side. We start with our uranium atom. This is called our parent nuclide, so that's what we're starting with, and it decays into thorium. Okay, also producing our alpha particle, our helium nucleus. So here, this is how we say we're going to write our helium, 2 and a 4. Now, how did I know that it became thorium? Well, our numbers must be balanced. So if we started with 92 protons, we have to end over here with 92 protons. We know that 2 of those protons are in our helium atom, so the other 90 have to be in whatever daughter nuclide is produced. We go back to our periodic table. Here is uranium, 92. We go back 2, and that's going to be thorium. So that's how I got thorium out of that one. Again, the most important thing here is that your numbers have to balance out. The law of conservation of mass and energy states that we cannot create or destroy matter. So we have 92 protons to start. We have 92 protons to finish. Same thing with our mass number. If we started with 238 protons and neutrons, we have to finish with 238 protons and neutrons. When we add those together, we get 238. Let's move on and see beta. Okay, so we're starting here with iodine, which is not past bismuth on our periodic table. It's 53, but this is an unstable isotope that it's going to decay. Its ratio is not 1:1 here, so more neutrons than protons. And remember we said that in this case, we create an electron. All right, so here is our symbol for an electron. We have that -1 and 0, but again, our numbers have to balance out. So our mass number, that's easy. We can see that 131 plus 0 is still going to be equal to 131, so we're good there. 54 plus a -1, we do 54 minus 1, that gives you 53. So here is our parent isotope and our daughter isotope. All right, so there's alpha and beta. With gamma, gamma emission usually follows other types of decay, so usually the isotope will go through alpha, beta, and then gamma. And I'm not going to require that you guys know how to write those chemical reactions for gamma, just alpha and beta. So why do they decay? Again, they decay because they want stability between neutrons and protons. They want to have that 1:1 ratio. When will they stop decaying? Well, they'll stop decaying when protons and neutrons are equal. So if you look at this graph, we've got protons on our X, neutrons on our Y. And this green line represents a stable atom or a stable isotope. Because if you notice, we have 20 protons, 20 neutrons, 40 protons, 40 neutrons, and similar going up. So protons are equal to neutrons. So the closer we get to that 1:1 ratio, the more stable our isotope is going to be. And here's some more examples. So there's the first two. Here's another one. This is our electron, or our beta emission. Here's kind of the opposite in reverse if we're adding electrons, what we can create. Alright, so some practice problems. Write the equation for the decay of plutonium-239 by alpha emission. And this should be on the back page of your notes. Oh, okay. I'm sorry, guys. I forgot to put Pu here instead of sodium. So just pretend that that's our Pu. Alpha emission, we know that, and so if we look at plutonium on our periodic table, we'll find Pu. Its atomic number is 94. Okay. So if we go back here, we have plutonium, again, Pu here, not Na, I apologize. 94. We know it's going to create a helium. So if we take 2 protons away, that gives us 92 as our daughter nuclei. If we look at our periodic table, 92 is uranium. Okay. Next question, what form of radioactive decay is occurring in the following reaction? If we look at our products, we see that it produces an electron, and we know that that must be beta. Here's another, identify the type of nuclear decay that is occurring. If we look, we started with radon, created helium, and so that must be alpha decay. So we're going to stop here and complete some alpha and beta decay practice problems. As you're doing the practice, please feel free to go back to the PowerPoint and use those examples. Good luck!